where we left off last time. And we're going to, in particular, focus on what's called the fundamental theorem of calculus, which is the shortcut for finding area under a curve. And to remind you what the theory says, or the theorem says, is that the area under the curve from a to b of some function f of x can be found by finding the antiderivative at b, subtract the antiderivative value at a. And capital F of x is called the antiderivative. And essentially, we're going to go over examples of these. Excuse me. Of these 20 questions. So, over here, I have a list of some standard antiderivatives. This piece of paper is a PDF in Canvas, so you can actually go and print it yourself. This top one is called the power rule, and basically it allows us to find the antiderivative of any power of x that you could think of. This bunch here are essentially antiderivatives of various cosine, sine, trig functions. There's our e to the x round, there's our 1 over x round. It doesn't have all of them. There are a few over here that I'll add to the list as we discover other functions that we need to find the derivatives of. So the first major chunk of questions, the largest number of questions that we are going to find the area under the curve. I'm going to change the name now. Instead of saying the area under the curve, I'm just going to say integral. So we are going to be finding integrals, and the vast majority of the 20 odd questions are going to be using the power rule. So let's find the integral from 0 to 2 of 2x squared minus 5x plus 1 dx. Now the first step is you find the antiderivative of this function. Now this is x squared, so the rule, the power rule as it's called, is add 1 to the power and divide by new power. So you get 2/3 there. Now this guy says negative 5x. If it helps, imagine that there's a 1 there. It is also a power rule. Add 1 to the power and then divide by the new power. Now, any number, in this case, it happens to be the number 1, but it could be 10, could be minus 20. Any number, in this case, just 1, the antiderivative of it will be 1x. If it was plus 5, the antiderivative would be plus 5. So I just use that as a special case. Whenever I find the antiderivative of a number, I just stick an x next to it. So this is our antiderivative. The way that we do the notation then is we do a vertical line, and this is pretty consistent throughout mathematics. You put labels, which is the start and finish value, a little bracket for emphasis. So antiderivative, a label from x equals 0 to 2, and basically you now plug in 2 here. So that's pretty much this piece here. So it's going to be 2/3 times 2 cubed, take away 5/2 times 2 squared, add 2, subtract 2/3 times nothing cubed is nothing, 5/2 times nothing squared is nothing, and add nothing is nothing. So normally when the answer is dead easy like this, I don't write down 2/3 nothing cubed, take away 5/2 nothing squared plus nothing. It seems pointless when I know that the final result is you're just going to get a whole load of zeros anyway. 2, 4, 8 times 2 gets me 16/3. 2, 4 cancel, take away 10, add 2. And in this case, we want to get the exact value. And exact values essentially mean don't have decimals, right? Just don't have decimals. So I'm going to have to combine those together. And I could do it the old-fashioned way of turning everything into thirds and combining them, and that would work. But I would much prefer that I didn't need to do that. So I'm going to let the TI-84 calculator do this calculation for me. So here we are. Are you looking at the TI-84? The reason I say this is that sometimes I think you're seeing what I'm saying, but you don't always. So are you seeing a TI-84 right now, guys?
Yes.
Yes.
Okay, we are ready to go then. So the calculation is 16 thirds. So you might not know that your TI-84 can do fractions. 16 thirds. Subtract 10, add 2. Now I'm going to hit enter and you're going to see a decimal. But I don't want decimals. I said, look, we need exact values in these questions. We do not want decimals because decimals involve rounding things off. And so we don't get an exact value anymore. So what you do next is you hit math, choice number 1. And choice number 1 says, take your answer and make me a fraction. So when I enter, it's going to take this answer and convert it to a fraction. So here we go, enter again, and there's your answer, -8 thirds. So if you didn't know your TI-84 can deal with fractions, it can. You just have to remember to hit the math button, choice 1, to convert your final answer into a fraction, in this case, -8 thirds. And we already know that that is a valid answer. It is possible for the area under a curve to be negative. And in this case, it was. Well, let's work on power rules that are less and less obvious. Suppose we do the integral from 1 to 3, and it's going to be x squared plus 4x plus 1 all over x. Now, in this question here, you can't start doing power rules. It doesn't work. You can't say, oh, power rule, divided by power rule. It just doesn't work. What you have to do, and this is much more common, is that you have to find a different way to write this. You have to find a way of writing this fraction as a combination of powers of x. And there are 2 different ways to approach this question. Both work. Right? The first way is to realize that you can think of this question as being a multiplication with -1. Now, if you do that, this guy times this guy gets you x, this guy times this guy gets you 4, and this guy at the end gets you x to -1. So what I have done is I've converted a fraction into individual powers of x. That technically counts as a power of x. And then, in this case at least, I have to change this guy into its equivalent form, 1 over x. Now, the reason that this one is a special case, you cannot use the power rule on x to the -1. The power rule says add 1 to the power and then divide by the new power. So let's do that at the side. Here is x to -1. If I use the power rule on it, I will add 1 to the power, which is 0, and then I will divide by the new power. Can you see that that's bad news? Because this is the only power of x. Right? It's the only power of x whose antiderivative does not work with the power rule. Now, return back to this question. Add 1 to the power, divide by the new power. 4 gets me 4x, And technically that guy gets me the natural log of the absolute value of x. I'll just call it log x. And I'll evaluate it at 1 and evaluate it at 3. So antiderivative evaluations. That now becomes 1/2 3 squared plus 4 times 3 plus the natural log of 3. Take away 1/2 times 1 squared plus 4 lots of 1 plus the natural log of 1. Right, that guy is 9/2. That guy is 12. And that guy is log 3. That guy is 1/2. That guy is 4. What number is the natural log of 1 equal to? The natural log of 1. What number is that?
0.
It's 0. So I won't, I guess I'll put it in, but I don't need to. Right, so we pretty much got all the pieces. I've got a 9/2. I've got a 12. I have a log 3. I'm going to take away that half. I'm going to take away that 4. I could have combined that in a different way, but too late now. This guy and this guy actually work well because you get 8/2, which is 4. And then you get a 12, and then you get a log 3, and then you take away 4. Oh, that's nice. They cancel out. And all I'm left with is 2 pieces. And that is the answer, because we want the exact value, and you can't do any more to 12 plus log 3. I'm certainly not going to go to my calculator and find out what decimal log 3 is. The final exact answer is 12 plus log 3, and we are finished. How about this guy? I want to find that integral. What do you think I need to do in order to be able to use the power rule to this guy? I mean, I can't leave it the way it is and try and do the power rule on it. It wouldn't work. Two x plus 1 squared. What do you think you would do? Any takers? Last chance. I can only use the power rule when I have powers of x. So if you tell me 2x plus 1 squared, that's no use to me. What I can do, of course, is find out what 2x plus 1 times itself is equal to. And if I FOIL this out, you're just going to have to take my word for it. We get that guy. Now that guy is ready to use. Add 1 to the power, divide by the new power. Add 1 to the power, divide 4 by the new power 2, and you get 2. And the number 1 gets you 1x. And then you can evaluate it at x equals 2 and x equals 4. And at this point, I'm just going to go dot, 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 dot. Because really all you do is plug in some numbers and then first answer, take away the second answer, and make it look pretty. So far, so good. Right. Let's see if I can bring some guys up. Here we go. Let's start making the questions even weirder. I want to find the integral of 4 square root of x. The only guy that I'm going to use is the power rule, which means this has to be written as a power of x. Well, square roots are fractional powers of x. So you need to be aware of algebra. You need to know that this thing, for instance, FOILs out. You need to know that this can be divided or multiplied by x to the negative 1 with the same effect. You need to be able to do those kind of manipulations. So square roots become half powers. A cube root becomes a third power, and so forth. Now this guy is ready to go. It's a bit messy, but you can do it. If you add 1 to the power, you get 3 halves. If you divide by the new power, which is 3 halves, it's the same as multiplying by 2/3. So dividing by 3 halves is the same as multiplying by 2/3. Now in this case, we're going to get 8/3 x to the 3/2. And technically speaking, that is the antiderivative of this guy. And it is. But we don't consider it to be in its proper format. I call this process, I just call it style points. We want these things to have a bit of look to them, a style to them. And the rules about how you write this guy down are quite simple. Your answer should, if at all possible, look like the original. Now, 3 halves is a fractional power. The original had a square root in it. So I want this guy to look more like that guy. So what I'm going to do is I'm going to realize that a square root is a half and 3 halves gets me that. So this guy is the equivalent of that guy. So that's a little bit of algebra that you have to be aware of. Fractional powers can be returned to radicals. Radicals can be turned into fractional powers. Both processes get used. Now, the advantage of leaving it in this format is that when we now evaluate it, it's going to be 8/3 the square root of 3 cubed, take away 8/3 the square root of 1 cubed. So that's 8/3 the square root of 27, take away, well, cube of 1's 1, cube root is still 1, right? So take away 8/3, looking good. And now style points. Does it look like the original? Yes. But there's a second rule. It should be as simple as possible as well. So that means you would never leave an answer as 4/8, right? You turn it into half. You never leave an answer as the square root of 8 because square root of 8 can be simplified to 2√2. So I'm looking at that 27 and I'm saying, I know who you are. You are 9 times 3. And the square root of 9 gets me 3. So what I have is 8/3 times 3 square root of 3's. Take away that guy. These cancel out. And now I have 8 square root of 3, take away 8/3. And that is considered the best version of this integral. So leaving it like this guy here is like leaving something half cooked, right? You haven't fully baked it until you've made it look pretty. So the rules for how your answer should finally look, the style point rules are: rule number 1, make it look like the original. So if the original has square roots, so should my answer. Rule number 2 is simplify whenever possible. Is there any questions so far? How we did? We good? This is a version of your homework, version 6. The variable that is used in an integral is totally irrelevant, right? This could be 4x squared plus x to 3 halves dx. It can be 4t squared with a dt. It can be 4y squared with a dy. As long as the variables are consistent amongst each other, they are all totally okay. Now, this guy doesn't need any work. It is ready to use the power rule. Add 1 to the power, divide by the new power. Add 1 to this guy, right? 3 halves, if you add 1 whole amount, gets you 5 halves. Dividing by 5 halves is the same as multiplying by 2/5. So there's your antiderivative of this guy. Evaluated at 0 and at 9. Now, style points, do you look like the original? Yes, you do. So as ugly as that looks, that's what it's going to be. Now, I'm going to have 4/3 times 9 cubed plus 2/5 times what, 9 to the 5 halves. Ooh, that's ugly. Take away, oh good, a whole load of zeros. Now, if you do this, 9 times 9 is 81, and 81, 9's cancel. God in Himmel, 3 81s, 12 81s, 720, 732 is what this guy gets you. This fella here, well, if you do 9 to the power of 5 halves, which I am now about to do, because I'm pretty sure it's a nice number, and I'm doing it on the calculator, so you just trust me on this. 9 to the power of brackets 5 halves. The answer I get is 243. So this guy is 2/5 times 243, which is not going to do much good because it's 486 fifths. And God, that's an ugly answer. Okay, so on my calculator, 732 plus 486 fifths, and then turn it into a fraction. Glad there's a calculator here. 4146 fifths. We do not write 18 and 3/5 or 7 and 2/5. All fractions have to be in this format, a single fraction. And that's the way we want the answers to be written in each situation. Is there any questions again? Are we so far so good? Okay, let's show you question 8. We have the integral from 1 to 9. We have 8 plus x squared all over the square root of x dx. And I can tell right away that that is no good. I need to change this, and I need to change it so that it can be written down as individual powers of x. That will allow me to do the power rule. So here goes. You probably don't need every single one of these lines that I'm putting in. First thing I'm going to recognize is a square root can be called x to the half. The next thing I'm going to do is that if you divide by x to the half, it's the same thing as multiplying by the negative of it. So these two terms are going to get multiplied by x to the negative half. 8 times x to the negative half plus 2 take away a half is what, 3 halves. We're done. So this guy had to be converted into individual powers of x so that we could use the power rule. They're not very pretty, but we need them. Now, if you add 1 to the power, so you get plus a half, divide by the new power is like multiplying by 2, so you get 16. Add 1 to the power, and then divide by the new power. You get that? So these are the antiderivatives. And then you evaluate at 1 and at 9. But I'm going to bring in style points. The original question has square roots. These fractional powers need to be turned into square roots. So what do we get? We get 16, the square root of 9, plus 2/5, the square root of 9 to the power of 5. Take away 16 square root of 1 is just 16, and 2/5 square root of 1 to 5 is just 2/5. Now that guy is 3, so 16 times 3 is 48. That guy there, if you trust me, you end up with 9 times 9 times 3, 243. So 243, 486 fifths eventually. And then at this point, I would just let the calculator finish it off for me. So it's going to be 48 add 486 fifths, subtract 16, and subtract 2/5. Then convert the answer into a single fraction, and it's 644 fifths. So this integral is 644 fifths. How are we doing, guys? Because I'm not getting a lot of feedback. Are we doing okay? Is there anything you want me to go over again? Is there an example that you're not sure what happened and how it happened? Oh,
I'm doing pretty good right now.
Okay. I like good. Right, so let's continue then and see. Each question gets a little bit trickier, a little bit weirder, whatever you want to call it. Now we're going to move into, I guess I'll call this one a trick question. Well, actually, not this one. This one is a straightforward question. Let's do that one. Oh, I can't see what I'm talking about. Let's do this one. No tricks. I bring this guy over. The antiderivative of e to the x is e to the x. So the antiderivative of 7 of them is 7e to the x. So nothing too weird, right? The antiderivative of this guy is that guy. And here's the guy I'm using, right? E to the x gets you e to the x. Now, plug in 7e to the 1, take away 7e to the 0. Well, all I need to do now is make this look pretty. Style points, simplification. You don't write e to the 1. When something is e to the 1 or x to the 1 or anything to the 1, you just call it 7e. What number is e to the 0? What's the value of e to the 0? Here's a number. Oh, I wasn't expecting that to cost trouble. 5 to the 0, 2 to the 0, e to the 0 are all the same. Okay, last chance. E to the 0.
E to the 0 is 1.
is 1. So minus 7 of them, you get that. There's your answer. Right? Nothing to see here. Here is a trick question. I'm even telling you it's a trick question. And I'll tell you what it's not. It's not E. The integral of e to the x is e to the x. That is true. But what is the integral of just the number e? Okay, while you're thinking about that.
1 minus e?
No. While you're thinking about that, the integral of the number 7 is 7x. The integral of the number 9 is 9x. What do you think the integral of e is? Last chance. Not e to the power of x, just ex. I know e sounds like it's important, but isn't e just a number like 2.7128? Like 7 is a number, like 9 is a number. It's no different than these two. It is just a single number being integrated. So the answer is e times x, evaluated at x equals 0 and at x equals 1. Well, e times 1, take away e times 0. Notice it's not powers, it's multiply. E to the 1 gets you e, take away nothing, and your answer, rather boring, e. So there's a little sneaky one for you. Here is another sneaky one. I'm going to do an obvious one first, and then the sneaky one. If I asked you to find the integral from 0 to 1 of x to the 4 dx, the power rule would say add 1 to the power, right, and divide by the new power, and then evaluate it at 0 and at 1, and yeah, off you go and get your answer. That's straightforward. X to the power of the number e is also the power rule. And even although the thing doesn't look nice, it's not like 4 or minus 2 or a half, it's still the power rule. And the power rule says you add 1 to the power, and then you divide by that new power. So the integral of x to the e is this weird looking guy. I won't bother finishing him off. Here's another one that looks even stranger. The integral of x to the power of pi. Pi is just a number like e, like 3/4, like 42. Pi is just a number. So the power rule applies here. It's x to a number. You add 1 to the power. Well, the way you indicate adding 1 is to say pi plus 1. You then divide by that new power, which is this guy, and then you can evaluate it at whatever start and finish values you are given. Let's take this one to the end. If you plug in 2, you get 1 over pi plus 1, 2 to the power of pi plus 1, take away 1 over pi plus 1 times 1 to the power, pi plus 1. 1 to the power of anything is 1. So basically that's all you get out of this guy. And there's really not a lot you can do with this fella here. So you're just going to call it what it already is. So that weird answer is the integral of x to the pi. I'm still using the power rule here. I'm just using the power rule where the powers are weird looking things, like pi or e or whatever it may be. So here's an example of a question where that happens. This is a version question 10. It's the integral from 0 to 1. 8x to the power of e plus 7e to the x. Now, although these two things look very similar, x to the e and e to the x, although they look very similar, they are treated quite differently. The antiderivative of 7e to the x is just 7e to the x. Now this guy here is x to the power of a number. E is a number. It's about 2.7182 if you want to know. E is a number. So the power rule applies. You add 1 to the power and then you divide by the new power. So that ugly guy is the antiderivative of the first one. This guy is the antiderivative of the second one. Now we'll plug in the number 1. So we have 8 over e plus 1 times 1 to the power of e add 1 plus 7 times e to the power of 1. Take away 8 over e plus 1 times 0 to the power of e plus 1. Add 7 lots of e to the 0. Well, we want to make this look as pretty as possible. So I'll start with the first term. 1 to the power of e plus 1. 1 to the power of 10. 1 to the power of 2 billion. Pick anything you like. 1 to the power of it is still 1. So that's basically 1. So this guy times 1 gets me that answer. E to the 1 is just considered as e. So there's the second piece. Now 0 to the power of e plus 1 is like 0 squared or 0 cubed. 0 to the power of anything is still 0. So these two guys get me 0. And e to the 0 is the number 1. So 7e to the 0s get me 7. And so the answer that we get here has 3 pieces. Piece number 1. Piece number 2, take away 7. And that is the end of that question. Are we good? I get a chat. See what's going on. One question mark. I think you were maybe answering this piece here. Yes, you're right. If you mean this is equal to 1, I agree. Here goes. 1 squared is 1. 1 to the 4 is 1. 1 to the power of half is 1. 1 to the power of e is 1. 1 to the power of anything you can think of is 1. Now, if you
I think
turn
it was
all
an
these,
answer to an earlier question, but that actually helps clear it up for me. So thank you anyways.
okay. Now, this guy here, if we make it zeros, zero to the power of anything is 0. Do you see, there's a very similar pattern. 1 to the power of a thing is typically 1. 0 to the power of a thing is typically 0. And both of those things happen here. Now, the next question is not that weird, but it's not a power rule anymore. Let's do the integral from negative pi upon 2 to 0, the cosine of theta d theta. Now, if we scan through our list, the antiderivative of cosine is sine. So it's going to be sine theta, so not power rule. And theta is going to be negative pi upon 2 to 0, which means we're going to have to find the exact value for the sine of 0, take away the exact value for that guy. Now, in Canvas, I have got this guy here. It's our unit circle. And whenever we have to find sine, tans, cosines of angles like pi upon 3, minus pi upon 2, whatever it might be, we need to refer back to this guy here. And so, if you want to find the sine of 0, right, which is not too difficult, the sine of 0, there's your angle here, has this coordinate 1, 0, right? So the angle 0 degrees or 0 radians has the coordinates 1, 0. The sine of that is the y coordinate. So the sine of 0 is 0. Now, if you want to find the sine of pi upon 2, you would go up to this guy here, and the sine is the y coordinate, which is 1. But I don't want to find the sine of pi upon 2. I want to find the sine of negative pi upon 2. And when we measure angles, we start off life on the x-axis, and we rotate either clockwise or anti-clockwise. The usual direction is pi upon 6, pi upon 3, pi upon 2, and so on. But if you go the other direction, you get negative pi upon 6, negative pi upon 4, negative pi upon 3, and negative pi upon 2 will take you to here. And the sine of negative pi upon 2 is in fact negative 1. And these two guys end up giving me 1. So the integral of cosine theta from negative pi upon 2 to 0 is the positive number 1. Let's see. Suppose I want to do the integral from 0 to pi upon 6. So I need my unit circle handy again. And the function I'm going to do it to is secant theta tan theta d theta. This guy here has an antiderivative. Can anybody tell me, can you remember what the antiderivative of secant tan is? Secant tan.
Secant x.
Well done. And the only change I'll make is they're calling it theta, so secant theta, but you're right. Now that becomes the secant of pi upon 6. Take away the secant of 0. So you might get all the way to here, and then you kind of fall at the last hurdle, because that's not the answer. We need to find out what these are equal to, and we need to use our unit circle. Now, if you want to get the secant of an angle, it's 1 over the x coordinate. So I'm going to look for pi upon 6. Do you see pi upon 6 is here, right? And the secant is 1 divided by the x coordinate, essentially the reciprocal of it, right? So the x coordinate is root 3 over 2, right? So 1 over that is 2 over root 3. Now, the secant of 0 degrees, well, here is 0. The x coordinate is 1, and 1 over 1 is still 1. So there's your answer. How are we doing, guys? Almost finished with these, but we didn't quite get every single one done, so that's fine. Let's just talk about a couple of questions rather than do them, and then we'll call it quits for today. Right, you're looking at question 20 here. 4 plus r in brackets all cubed. This is eventually going to be the product rule. That is product rule, the chain, the power rule. Finally got the right name out. What will I need to do to 4 plus 3 to the power, 4 plus r to the power of 3 in order to find its antiderivative using the power rule? What will I do to it? Last chance. Well, we did one earlier today that was similar to this. Do you know you need to FOIL it out? Just as a little bit harder. You need to go 4 plus r times 4 plus r, get that answer, and then multiply it by another 4 plus r. And our last question, what would we do with question 21? We've done 2 like this. How would I rewrite 21? How would I do it?
You would make it so that the v to the power of 4 would be v to the power of -4, put it on the top. So it'd be v to the 3rd plus 3v to the 6th plus v to the power of -4. And then you
Times
can
v to the
change it
negative
all.
4. Yeah. Times
Oh,
t to
yes.
the negative 4. Yeah. And then just multiply it out and off you go. Yeah.